My name's Ben Evans, and this evening I'm going to be talking about my new book, The Well-Grounded Java Developer, which I'm writing along with Martin Verberg and Jason Clark. And we're going to be tackling that topic that is, I think, of perennial, everlasting interest to Java developers, which of course is going to be performance. And performance is a subject that I have been interested in and in love with for, I guess, for many, many years now. And it really is at the heart of so much of what I've done in my career as a Java developer. So it's great to be in a position to be able to take some time this evening and talk about it. You know, because so many developers have this attitude or this opinion about performance, which is really not very similar to the way that it works at all. You know, people think that performance is some kind of, I don't know, special magic spells that you can find to make your programs run really, really fast. You know, I often get questions when I'm teaching performance about things like, you know, which is faster? Is it better to use streams or is a for loop faster for simple operations? And, you know, that those are kind of really the wrong questions and not actually that helpful when we're actually dealing with performance. Well, I know that developers always want to see things for themselves. So let's actually get into it a little bit. What I'm going to do is there's a project which is actually up on GitHub. I'll put the link up at the end, and we're going to look at a couple of simple examples just to get going with. Okay, so the first of which is this caching example. Let me just check that actually this is streaming through okay. And yeah, okay, great. So what we're looking at is this class is very simple. It's called caching, and in it you can see that we just do a very, very simple setup. I should probably do is bring that down so I'm not constantly staring up there at it. There we go. So you know you need to see it. So I actually need to leave that there. So I'll just put it with me looking up at the code as I'm talking to you. Our main part of the code here is controlled by this array test data, and test data is pretty straightforward. It's an array of ints. So there are just over 2 million. I've used 1024 times 1024 instead of a million just because it's powers of 2 and it kind of makes the maths, well, if not easier, then easier for the computer. You know, humans prefer 10 bases and humans and computers prefer base 2. So yeah, so this is a nice even power of 2 to make life easier for the computer. So we have an array called test data. And then we jump into this class. You know, down here we've got the main method, which basically just dumps us into this run method. There's a bit of code here. You can probably see this. Don't worry about what that does. I'll explain why that's there later. And then we actually come on to the main part of the program where we print out line and item. And then what we're going to do is we're going to drop into this for loop. And this is just like the world's simplest, most boring style for loop that you can imagine. And we're going to do 100 iterations. So just from I equals 0 to less than 100. And you know what? I'm actually going to change the code a little bit here because I actually have been writing a fair amount of Rust lately, if anyone's played with the Rust programming language. And what that has taught me is that I actually don't like the increment and decrement operators anymore. They actually are a source of bugs. So whenever I find a piece of my Java code like this, I'm actually just going to modify this and actually, instead of saying I++, I'm actually converting this to the statement I equals I plus 1. It's clear, it's unambiguous, there are no side effects, there's no cleverness that I'm relying upon. It's just, it actually makes it, I think, easier to understand. And, you know, it's kind of a good example about how when you start programming in more than one language, you know, you can actually have different techniques which come in to influence the way you write code, and it propagates back into the code you write in other languages as well. Okay, so yeah, so that's my code for the for loop, and what we're going to do is in each iteration through the for loop, you know, you can see this probably block of code here, and you can see the repeated calls to system.nanotime. Now, if you're not aware, then you maybe you know this, maybe you don't. But with system.nanotime, you have to always have pairs of calls. You can't really make any sense out of making a call to system nanotime by itself. It just doesn't really mean anything. Yeah, because what it actually does, at least on Macs and Linux, is it reads a counter from the CPU. And when you switch your computer on, you actually don't know where that counter is initialized. It's not synchronized to the system clock, the wall clock, or anything else. It's just a random number. But no matter where it starts, it continues to increment. So every nanosecond or every time the processor clock ticks, this counter is incremented. So you can use it to get a very high precision measurement of how much time has elapsed from a given starting point. So you put the nanotime calls in pairs like this. So like this first one here is T0. And let's just zoom in a bit. There we go. Maybe we'll just get rid of this. We don't really need the project open as well. So how's that? That's looking a bit better. So we set up T0. We call this method called touch every line. And then we also call touch every cache. And these methods are down here, which we're going to meet in a second. And then what we're going to do is we're going to time them separately. So we need to bookend each of them with these calls to nanotime to get these answers back as to how many nanoseconds each method took to run. And then we're going to get these other long values, which is EL every line and EL every item. And just by subtracting the two values from the nanotime. So pretty low level and pretty low tech. But what it's going to give us is it's going to give us the times that the every line and every item method took to run. And we're going to print out 100 of those. So I'm just going to run this and we'll just see what happens. In the meantime, I'm just going to take the opportunity to check the chat. See if there is anything happening. Okay, so it's still starting to run. It takes a little while, and then as you can see, it runs through really quickly like this. Once it's actually got past this, because of course there was a hidden bit of code here which doesn't actually output anything. It just runs those methods repeatedly, and you might very well be able to guess what it's doing there. If you can't, then I should say that it's for the JIT compiler. So it's there in order to allow the JavaScript compiler to warm up fully and to actually see what's the methods as they actually are after JIT compilation. This means that the methods are running as fast as they can, and there's no inconsistency in how they're running later. If you don't warm up, then you get numbers which are not correctly calibrated, and that's generally not super helpful. Okay, so let's look at the numbers we've got here. Let's zoom in on these as well, and that's gonna show us some interesting results here. So one of the things we have is that if we look carefully at every item and every line, we can see that what happens is that and again, I'm going to make my change here. I'm going to make this I equals I plus 1, and just I equals I plus 16, just to make it very clear what's actually happening. And IntelliJ has helpfully rearranged those, so let's just rearrange both of those as well. And then, let's just get rid of those increment operators, because I think I'm actually kind of overusing them, or I'm over the use of them, let's say. Yeah, so you can see that it's the same statement that is happening for each of these elements. There we go. And this one, touch every line, you see is only incrementing. Well, it's not hitting every item. This one, which is kind of where the name comes from, it's actually incrementing every single item that's present in the array. Whereas this one is only doing every 16th element, and that's kind of a little bit strange, because what it means is that this method is only doing 1/16 of the work, right? It's only incremented a 16th of the elements of the array by the time that it reaches the end. And yet, and by the way, there's no trick here. It genuinely only does increment 1/16 of all of the elements. There's no hidden get out clause. It actually does only 1/16 of the work. But when we look at the timings, you can see several things. First of all, you can see that there is actually quite a lot of noise and jitter in these numbers, and we'll come back to that. And then the other thing that you can also see is that if this was true in the sense that we're expecting it, and every item should be running for 16 times as long, you would think. You're doing 16 times the work, well, you should run for 16 times as long. And that's not happening. Yes, there's some variance, but look, there are numbers like this one here where they're basically running for more or less the same time. So we've got 69 and 62. We've got 56 and 50. We've got 62 and 59. And in fact, in this case, 62 and 59, this one is actually running faster. Sorry, the line is actually taking more time to run than the every item. So the every item is running faster than every line, which seems, really quite unusual and quite crazy. It's just like, well, how could that be happening? And then you can also get down and you can see that this method can run in as little as 44. I mean, let's work the units out here. So this is nanoseconds. So that's 443,000 nanoseconds, and 1,000 nanoseconds is a microsecond. So the method can run in as little as 443 microseconds, which is kind of incredible. That's a really small amount of time. But then it can also take as long as, 137. Well, that's not 137. That's 1.37 million nanoseconds. Right? Now, a million nanoseconds is a millisecond. So that's 1.37 milliseconds. So roughly 3 or 4 times as long. And look, there's one down here which is even more than that. That's actually 2.14. That's 2.14 milliseconds. That's really quite a long time for such a simple little method to run. And you might say, oh, there's potentially all sorts of other things going on. Well, you might guess at things like garbage collection. And, that would be a good guess for most programs. But as you can see, I don't actually create any new objects here, at least not in these little methods. All of my object allocation is done up front. I create the array of test data. And sure, we loop over it and we modify it and we do a lot of reading and writing to memory, but we don't create any new objects. So this is also immune from the effects of garbage collection. In practice, writing these types of benchmarks is actually really, really difficult, and it's not easy to get them right. So I normally recommend that people don't try to write them themselves, and instead that people actually don't look this closely at the detail. The reason I'm doing it today is just to show you that these variations and this weirdness in the numbers really exists. So there's a lot of noise here, and there's a lot of things which can go on to cause this noise. But the big takeaway that two big takeaways really. One of them is Java performance numbers at a low level are really noisy and really messy, and you have to be careful how you handle them. That's the first takeaway. The second one is actually this puzzle, this mystery of why the numbers are so similar in the first place. It seems strange. It seems, why would you have numbers which are so similar when on paper, at least in code, this one looks like it's doing hardly any work. Okay, well, let's explain what's actually going on here. When you ask a program to access memory, especially memory in an array like this, you don't get a single byte of memory at a time. Instead, modern hardware provides you a chunk of memory which consists of 64 bytes. So rather than just modifying a single int or loading a single int at a time for modification, you are actually getting 64 bytes of memory at a time from the silicon chips that make up your computer's memory. Okay, and that number 64 turns out to be important, because notice that I've carefully chosen the number here to be 16. And ints in Java are 4 bytes, and 16 times 4 is 64. So the trick that I'm exploiting here is that actually, even though I only increment every 16th element, I still fetch the entire array. So the hardware still has to physically respond by sending all of the data, the whole 2 meg, over the computer's memory bus. Okay, and that is basically all of the work of the program. The work of the program is not in incrementing individual elements. The work of the program is transferring the data from main memory to a place where the CPU can act on it. And that's a little surprising to a lot of people, that we can have this situation where we can, we have what looks like a much larger amount of work, and actually it's done in almost the same time, and perhaps even in more time than it takes to do less work. Now, just to show you this, I'm actually going to change the number around here. I'm going to rerun this. I'm going to put the increment up to not to 1, but to by 64. And now what's happening is we're going to miss out a few of those chunks of memory. They're called cache lines. At this point, I now don't need to actually receive every cache line for this second method, because I'm jumping ahead by 64 bytes, 64 ints each time. So that means that I only need to receive 1 in 4 of the computer's cache lines that make up the block of memory which corresponds to this array. So let's rerun this and see what happens. Now, we're expecting to see a decrease. We're expecting to see the amount of time taken to read every line to be significantly less than touch every item this time. Will it be that factor 4? Because if my theory is right, it should be about a factor 4. It's not actually going to be that. As if we look carefully at these numbers, then what we can see is, once again, let's do the zooming in thing and upsize this window a little bit. The every line, so the left-hand column is, well, sometimes it's a factor 2, sometimes it's a factor 3. But in pretty much all cases, it seems to be coming in significantly less. There are some outlier points like this one where it comes in at 477 microseconds, and every item is about a factor 3, and it's quite a lot larger. But in general, there seems to be about a factor 2 or factor 3. Yeah, there's a definite signal here now. I mean, we can plot these numbers, and I've actually been playing around with a Java charting library, but we probably don't have time to do that today. But maybe on a future session, I can actually plot these numbers and just show you how noisy the data is. But even without doing the plot, you can still see that there is very definitely a signal here. There is very definitely an effect, and that changing the every line method to not receive all the data, to not require all the data to run the method, has had an impact which has substantially changed the performance characteristic of the individual method. Okay, so there's actually a picture. I've got a thing that I like to show, which I think conveys this pretty well. And that's the book cover. And this is what I sometimes call my scary clown diagram. Okay, because it looks a little bit like a scary clown. We have the eyes, which are the gray circles. They're actually the CPU cores, of course. And we also have 3 levels of CPU cache: level 1, level 2, and level 3. And those are the green, yellow, and orange levels of cache showing on the diagram. We also have the physical interconnect, which is called the North Bridge, which connects the CPU to main memory. And I've shown the North Bridge here as a dotted line. You might also be able to see, if you look closely, there are a couple of other CPUs that I've also shown in kind of a ghostly, shadowy grey colour, which are also present on the North Bridge as well. That turns out to be quite important because the North Bridge is shared. It's shared between all of the CPU chips, and it's shared between all of the processing cores which are present on each individual CPU chip as well. So that means that the bandwidth of the North Bridge is a really, really important part of how the computer operates. It's actually one of the most important performance characteristics of all, and it's always surprises me how few people actually know what the bandwidth of their North Bridge is. The reason this is so important is because if I'm going to do anything on a program, and bear in mind, we're down way deep in the hardware here. We're not talking about Java or C++ or any specific programming language. What I'm talking about here is about all programming languages. We're talking about the fundamentals of the way that a computer executes code, and we're below the language, we're below the Java virtual machine, we're below the operating system. We are down at hardware level. So a lot of what I'm saying here will also be true of other languages, good languages, which are able to take advantage of the hardware. But the absolute hardest you can push any language in terms of, say, allocating memory or creating objects is governed by the North Bridge. You just can't push the hardware any faster than the North Bridge can go. So, for example, if you are executing code on the CPU core, which corresponds to the creation of a whole bunch of objects, well, those objects are going to be allocated in the L1 caches, and then that's going to have to flow back to main memory. It's going to have to flood back across the North Bridge. So the speed of it, the actual time taken to get those allocated objects, the ones that have been set up and prepared, across the North Bridge, that takes time. It's not an instantaneous operation. And the absolute maximum rate that you could allocate objects is determined by that speed of the North Bridge. So you might take a guess. I mean, it very, of course, now depends very much on your hardware. But on modern hardware, you would expect to be able to allocate several gigabytes per second, and that's kind of a decent benchmark. I mean, in general, I have different rules of thumb for allocation rates, and hopefully a bit later we're going to talk about Jfr Flight Recorder and Mission Control, and I'm going to show you some actual allocation rates that I have on my machine, and we can talk about points where I would start to investigate things. But in all cases, you can't beat the laws of physics. You can't beat the speed of transfer that's possible across that North Bridge. And remember, this is a shared resource. So, and not only is it shared, it's shared at the physical level. So if you have multiple virtual machines sharing the same physical infrastructure, as we do, for example, in the cloud, this is subject to noisy neighbor problems. So this is the idea that if you have virtualized containers, they still have to run on silicon. They still have to run somewhere. And if you have two applications in completely separate virtual containers, which are running on top of the same hardware, and both of them are allocating a lot, they may feel the effects of the other container that's running, because they are oversubscribing. They're trying to push too hard on that shared resource, which is the North Bridge. So this is, you can never truly, as much as we might like to, abstract away and have Docker and Kubernetes and virtual environments, that they always run on top of real computers. And those real computers have hardware resource limitations, which you can never truly get rid of. So the point of the scary clown is just to show you that the computer's hardware and its resources are also an important part of how we would think about performance. Before I started streaming, I bet not many people, if I'd asked, would have said, "Oh yeah, the North Bridge is one of the most important parts of a computer's architecture." Okay, and then just because I know that people really like to see numbers, let me also just pop up this slide as well, which is just me talking about the different speeds of memory. And this, of course, is color coded. It's color coded to the same colors we saw on the previous chart. So the green, the level 1 cache, is all about four instructions, really, what's needed to access data that's stored there. And then we've got the yellow items, which are more like 11, I would say, 11 cycles, and then orange is 14. But then there's this huge drop-off of 167. And I think I got these numbers from a paper by Google. And if I'm remembering correctly, Google actually do quite a lot to ensure that their hardware has quite fast main memory. So I think that for the computers that you use, the numbers may actually be even worse. You may actually be looking at 300 or even 400 clock cycles in order to get data back from main memory. So there's a lot of that gulf, that difference between keeping things in cache versus bringing things across from main memory is huge. And this kind of leads us on to the idea that if it's so expensive to get data from main memory, then the main performance characteristic, if you like, what I would call a first order performance characteristic, is really how effectively can we use the cache. So what is it that we can do in order to make applications cache friendly? And a lot of the design of Java and Java applications is to try to be sympathetic to those parts of the machine, and especially to making sure that applications data stays in cache as much as possible. And by cache, I mean the CPU caches. I don't mean some kind of in-memory cache or something else that you might have. Okay, so that is the first thing. So this is just a simple discussion about caching and just how CPU architecture affects us, because that's the truth about where we are. We live at the end of the age of Moore's law. We no longer can rely on the fact that hardware engineers are going to come up with better and better and faster chips for us. Instead, we have to start getting used to the idea that for an increasing number of applications, if we want to get better performance than they come with out of the box, well, we have to do some work. We have to start thinking about performance as part of the core job of an engineer. Okay, so far so good. Let's take a look at another example. I think this one's quite fun. So let's just do this here. Just bring up the other example I'm going to show now, and this one's called string hash. And okay, so let's just upsize this a bit. Again, pretty simple program. So let's just talk to it a little tiny bit before we dive in. And what I'm going to do is in this run method. Again, I really should fix these. Yeah, I'll just do that as well. So in this part of the loop for the run method, we're going to call this auxiliary method, this hashing method, and it's got two parameters, an int and a char. And when we get into the time hashing method, you can see that what we do is we take the length and we take the individual character. This time we do create a string builder object, and the string builder object is there because what we're going to do is we're going to repeatedly call the append method on the string builder, and we are going to append 1 million copies of the char that we passed in. So the char we're going to pass in is x. I mean, it doesn't have to be x; it can be anything. And then that we're going to generate a string. So when we pass in I equals 1, we're going to generate a string of 1 million x's. When I is 4, there's going to be 4 million x's. It's quite a large set of strings that we're creating. And then we're going to create a string object. And then what we're going to do, oh yeah, and I just need to probably just combine these. So we've got that and So we're gonna take this huge string of millions of characters, turn it into a string builder containing millions of characters, turn it into a string, and then we are going to use a nanotime method that we saw before, again to take two nanotime measurements, subtract one from the other to give us the duration of how long it took us to actually calculate the hash function. Okay, so far so good. Let's run this and let's see what we get. Did that fail to start? It may have done. Let's try again. Now this time you see there's no warm up, right? We don't do anything to warm anything up. And I don't know if you can look at this, but you can notice that if you can just time it, it's taking a little bit longer each time, right? So now we've got up to sort of 70 something, 80 something, 80 million characters, and it's now taking. Well, I'll just scroll back. It will keep doing them. I mean, it's not as obvious down in the low numbers, but once we get up to about 23 for like 21 million, 22 million to 24 million, 23. And what is that? Yeah, so that's 25 million. So 23 million length string took roughly 25 million nanoseconds. So there's a roughly linear scale. It's not perfect. Some values are lower and some values are higher, just like as we saw in the caching example. This Java performance data is really noisy. So as we go down, though, you can kind of see that it's maintaining this sort of rough linearity, if you like. But the actual hash values don't matter. I just included them because, for the sake of argument, really. And the more time we go through, we start to see that we actually get a few outliers. It says 132 took 146. There are probably some larger outliers waiting for us as well. You see, now you can really start to see the duration on these. And that one took 178. So now what's happening, as you might guess, is that actually there are some of these that are being affected by garbage collection. So that's because we are actually creating objects on each pass, right? Every time we call time hashing, we actually construct two objects, one of which is the string builder, which we don't pre-size. And why is that important? Well, because if we step in here, so the string builder is going to be backed by a, let's let that slowly tick around. It extends a class called the abstract string builder, which is kind of where the action happens. Because buried inside there is a byte array. And we don't provide an initial capacity. So it starts off with effectively an empty string. And when we call append, just use the F7 menu here just to find the append method, and I think we'll just order these A to Z, because what we're doing is we're appending a char, so we can jump straight here. And there is one of these things which says ensure capacity internal. And if we are overflowing the capacity, we increase to a new array each time. So whenever we overflow and we run out of space, we actually create a larger array object. So there is going to be quite a lot of object allocation because we're appending a single character at a time. So when we work with the string builder, we're actually doing effectively the maximum amount of allocation that we'll expect to see. And then, of course, when we convert it to a string, we make a final copy of of that as well. So there's a lot of copying which is going to go on there too. So it's perhaps not surprising that the string builder part and the generation of the string takes a bit of time and consumes a bit of memory. But look carefully, we don't actually include that in the nanotime. The nanotime measures from there to there. So even though there is a certain amount of time which goes on to do all that string construction, it's not being measured. Instead, it's only the call to hash code which is being measured. And that might surprise you. It might surprise you that the time taken to run a string's hash code method depends upon the length of the string. And this is one of my favorite bits of trivia, and we have a couple of minutes, so let's actually dive into this a little tiny bit. There's two things which you need to know in order to understand why this behavior exists and why the string has a linear runtime in its hash code. Firstly, that sounds a bit strange, right? Because normally when you think of hashing in a classical computer science sense, what people are thinking about is an order one algorithm, which this is clearly not, right? This is not designed to be order one. It's now taking, it's ticking over in, I guess, about a number of seconds here. So this is now not a constant time algorithm for developing the hash code. So what that means, first of all, explain why the hash code has to run in linear time, and then we'll talk about what that implies, what the existence of the linear time hash code implies for the design of string. The first thing is that the string hash code has to be linear. Has to be. Because consider the situation, where you have two strings that only differ in the last character. So in our example, we've got a string of millions of x's, and imagine that you have another string which has millions of x's, and the last x is replaced by a y character instead. Okay, so x for millions of x's, and then a y at the end. That string has to have a completely different hash code to the one that's just all x's. That's actually one of the definitions of a good hash function. This goes all the way back, believe it or not, to 1948, to Claude Shannon, the father of information theory, one of the absolute dawn of time in computing terms. And Shannon's actual definition of a hash function, a good one, in modern terms, what we would say is that if you flip one bit of the input data, roughly 50% of the output bits flip. Now just think about that. Think about that. Just interpret that string of bits as a number. So what it's saying is that the output number is an unknown amount far away from between the two strings. The one with all x's gives you one value, and then the one which is different by just one character is almost as different as possible. It's almost the complete opposite of a linear function. If you studied some maths, you know that when you put a number into a linear function and you add a little tiny bit, you change the input by a little bit, you get a tiny change in the output. But that's not what's happening here. It's not what's happening. Instead, we make a tiny change in the input and we get a vast change in the output. And the reason why, of course, is I hope a little bit obvious. We don't want hash values to be similar for similar inputs. The whole point of a hash function is it's supposed to be one way. Given an output, we're not supposed to be able to recover the input value. But if we had a bunch of vaguely similar texts, inputs, and we know that the hash function only changes a little bit when you change the output, you could use that to construct a scheme to go backwards and to break open the hash function, which you don't want. So for a true hash function, you can't do that. The outputs have to be as different as possible. Okay, so go back to the example of a string. You have all of these x's and then one y. What this means is you can't compute the hash value without looking at every character in the string. And if you can't compute something, without looking at every element of it, it's linear in the size of the object you're looking at. So that's why. To have a good, safe hash function, we are required to have a hash function for strings which is linear in the number of characters that are in the string. Okay, that sounds good. So let's do the next bit. Why does it produce this linear behavior? Well, because we have to evaluate the hash code. And that leads us on to our second surprise. Because if we open up the string class, you will find, oh look, we have lots. So there is the value, which are the actual characters of the string. There's also this final bytecode coder. But notice that the hash code is not 0. It's not final. So it defaults to 0. And then there's also this other field which also says we need to actually cache that the value actually is 0, because obviously we're storing this as an int, so we don't have an equivalent of a null value. So we have to default it to some primitive value called 0. But when we actually calculate the hash function, it might actually hash to 0. So we now have also the secondary Boolean field to say, hey, there's 0 in the hash field, but guess what? It actually means that the hash value actually is 0. Okay, so far so good. And now let's call hash code. And the first time we call this method, we read in the value hash into the field h, and notice what it says. The hash or hashes 0 field are subject to a benign data race. What does that mean? It means that 2 threads could both start to calculate the hash code at the same time, and they must come to the same answer. Because here is the secret that's hiding here. The string, despite what you've been told, is not actually immutable. You know, it has a mutable field. Right up at the top, we found a mutable field. Here it is. It's mutable. When you create the string, it has not set that field yet. It does not set it over the entire lifetime of the string unless you call hashcode. So the string is not actually immutable. It is only effectively immutable. And the detail and the verbiage around what's said at the start of hashcode about benign data race is there to indicate that although it is mutable, it's not the case that different threads can come to a different answer about what the hash code of the string is. They may waste some processing time by both calculating it when only one of them needs to. Because if you look at this piece of code here, you can see that what happens is after you've calculated it once, you always keep it. So basically, the first time that you call hash code, the value is calculated, and you save it in the hash field. And after that, you always return the same value. So that's the other little secret I wanted to show you, is that the hash code of a string is only determined the first time you call it, and strings are not actually immutable, only effectively immutable. So just some fun playing with a couple of simple little performance examples. Let's do something a little different now. What was I going to talk about next? So we talked about the noisiness of data. We've talked about the speed of memory. And what this is showing us is that it's very important that we measure things properly. My old buddy Kirk Pepperdine always says, measure, don't guess. And that, I think, is a good maxim to live by. You know, we wouldn't have I think suspected the behavior of the string hashcode method if we hadn't just had a play with it and had a look at what's going on. And it's also true that we need to have a sort of model for how we think about performance. You know, would we've expected the behavior of the caching example and the scary clown diagram if we hadn't thought about how a computer actually operates. And as part of that, one of the other examples is, you know, to get up away from the hardware a little bit, is just to think about, do we have a model for how the JVM looks like? If you don't, here's one I use a lot. This is my interpretation, my mental model of what the modern JVM looks like. You can see that there are two very distinct phases here. There's a class file creation phase over here, where we take our source code and we turn it into a class file. And then over here on the right-hand side of the diagram, we actually have the runtime. We have the execution of Java code, which is what I'm showing here. It starts off with the class loader, which is where all Java classes must pass through. The application class loader, which is what typically your classes will use, is a little bit different to the one that's used to load the system for performance reasons, but in both cases, it passes through a class loader. And this is where Java's security model is primarily implemented. You do a lot of checking in the class loading phase in order to be able to avoid runtime checks later. So all the guardrails, all the safetiness of the Java language that you think about, like not calling private methods or not being able to call a method with the wrong types, or a lot of the static typing that you think of the Java system is implemented in the Java, the source code compiler, and in the class loader. That's where a lot of the static type system lives. At runtime, the JVM actually is mostly just objects. It doesn't see the static types very much anymore. Okay, so then we take the code and we put it into this method cache, and this is more of a conceptual version than any subject specific piece. There isn't one area of memory within the JVM's address space called a method cache, but I think it's a nice conceptual model, just to say, well, okay, there's a place where the methods from classes that have been loaded live, and they're just stored there as bytecode. So bytecode is just the instructions for the Java virtual machine, and they're stored pretty much as is in the method cache. And then we feed them into this blue, which is the interpreter. And the interpreter basically runs and executes code. It finds more methods that it wants to execute. It loads, it executes those, etc., etc. And you know, your program can run in that state for, well, indefinitely. You don't have to JIT compile. You don't have to do anything else. You know, you can just execute methods happily within the interpreter. But notice how it's structured. Notice that it's the class loader, so you have to provide a class. You can't just give it some random bytecode outside of a class. The hierarchy and the structure of metadata, which goes along with the class file format, has to be obeyed. Methods have to turn up packaged in the way that we expect for class loading. So the interpreter executes the methods, and then on many different JVMs, there's actually another subsystem, which is the JIT compiler. And the JIT compiler is just sitting and watching all the time everything which is happening within the interpreter. We have a question in the stream chat. So the stream chat question is, hello, I'm just learning with Java. Can I ask questions? Yes, please, by all means. Please ask questions in the stream chat. And if other folks are on the line and want to answer them before I can get to them in the chat, please do. And if not, I'll periodically check back into the chat, and then I'll answer them on the stream if I can as well. So we were just talking about the JIT compiler. So its first job is to watch, and it's to perform profiling. One of the other the ways that we can talk about JIT compilation, there's a phrase which is used, which is profile guided optimization, or PGO. And I need some water. And PGO, profile guided optimization, is a way of determining how to optimize code based not on what the developer tells the compiler to optimize, but based on the observed runtime characteristics of the code. So the interpreter is running, it's executing code, and the profiler is watching. It's watching which methods get executed. It's watching things like what types and what values are being executed. It's watching things like, if there is an if statement, which branch is taken? Or if we call a method with an interface, is it actually always the same implementation that's seen at that place where that call occurs? So all of that statistics gathering is taking place in the profiler. And at some point, the profiler decides that certain parts of the program, specifically certain methods, are now in a place where they can be called hot enough. That's kind of where the Oracle and OpenJDK VM hotspot is where it gets its name from, because they are the hot spots of the code. Yeah, that's kind of what passes for programmer humor. What can I tell you? I'm very sorry. This is not a profession in which you expect great comic talent. So hotspot is based around this idea that there are specific parts, specific methods in the code which are going to be called more than others. And then what happens is those specific places, that's where the optimizer and the emitter spend their time. It's a trade-off. It's a statistical gamble or a bet that there are some parts of the code which are so much more important because they are called so much more often than others that you prioritize them rather than spending time trying to compile everything. You compile and heavily optimize the important parts, and that spending your effort there pays off much better than trying to optimize everything. And for a large number of workloads, that actually seems to be true. It seems to be the case that you can just pick the hot methods and compile those. Because what tends to happen is if there are only a few hot methods, if you just compile everything blindly, you're actually wasting a lot of resource. You're tying up your compiler, because remember, the compiler is operating at runtime. So it is using up resources which could be being used by your program code. So everything in the blue box is your program executing, and everything in the red box also requires CPU resource, but it's not directly helping the program to actually process work. Now, it may do if you can replace some bits of the program with supercharged versions of it. It may well help, but there is a trade-off there. You have to balance the sacrificing of some of your resources so that the JIT compiler can work against actually making forward progress in your program, which is running in interpretive mode. So that's what profile guided or JIT compilation is all about. It's about making that trade and saying, okay, well, maybe by focusing on the most important parts, maybe there are some big gains to be won. And mostly that is pretty true. That is how that is what we see. And it's not just Hotspot or Java. Many languages have a JIT compiler, and the idea that profile guided optimization or that there is a small percentage of the code which is important compared to a much larger body of code which is not as important and probably can be ignored, is a pretty well established principle in software engineering now. Okay, so slightly off topic question in the stream, but why not? I'll answer this one. Explain the static keywords: static class, static method, static variable. So the thing to remember about Java's keywords is that they are actually often used in very different ways with a kind of linking concept. In the case of static means different things depending on what we're talking about. A static method means that the method does not need an instance. Yeah, so objects, instances, contain data and they contain, which we call fields, and they contain methods. Now, if you don't refer to any of the individual objects data, because you don't need to, then you don't really need an instance of the object in order to call that method. So it kind of seems silly to create an instance of an object, an instance of a class, to create an object to call a method on it when you don't actually depend on any of that object's data. Yeah. However, it might well be the case that from a logical and design perspective, that method belongs with that type. So if it's related to those objects in some way, but it doesn't depend on the data of any specific object, we need a way to kind of keep it together with the things that it belongs with. And that's what static methods are. Static methods are they're things which belong alongside the objects of that type, but don't depend on the details of any specific object. So we call them static methods, and then they live in the class with the static keyword, and they then can be called without needing an object of that type. You just call them directly on the class instead of on the object. And a static field is the same idea. It's data that doesn't belong to any specific object, but still belongs together with the type. So that's those are two examples. Static classes are a little more off topic. They're kind of they're used for inner classes where you don't have an owning instance. Is how they are typically used. Okay. Okay. All right. So another interesting thing from the chat. So Yagram is asking, it's always intrigued me, given the time difference between CPU cache and RAM, why Java opts for a heap model where everything is a reference? Okay, so what you have to realize is that everything depends upon transistors. And transistors are a finite resource. Almost everything in performance is about figuring out what the finite resource is and what is competing for it. On a CPU chip, I mean, you can do the maths. There's a famous paper called "The Free Lunch is Over" by Herb Sutter. And that kind of gives a good insight into some of the the trade-offs which are present. You have Moore's law with this amazing explosion of transistors, but even despite that, and we're up into the billions of transistors now, it's actually quite difficult to get very much cache memory onto a chip. You could maybe get let me work this out. So each bit of cache memory costs you 6 transistors. Okay, which doesn't sound like a lot, but what that means is that to get 1 meg of cache memory, you need roughly 48 million transistors. Okay, so to get 10 meg, you need 480 million transistors. And how many transistors have we got on a chip these days? Well, let's be generous. Let's suppose it's 5 million. Sorry, 5 billion. Yeah, 5 million was about 30 years ago. Let's suppose it's 5 billion transistors on the chip. Well, 480 million of them only buys you 10 meg of cache memory. Okay, so you could say, okay, well, let's turn that up again. Let's go all the way up to 480 million transistors. So all the way up to 100 meg of memory. Well, that's eaten 4.8 billion of your transistors, and you only have 200 million transistors left. So you haven't got a lot of space left for CPU cores or any of the other things that you need to build out of your transistors on your chip. And in fact, the trade-off point is a lot lower. So you just can't make the CPU caches very large. That's quite often why they're measured in kilobytes. I mean, sometimes they're measured in megabytes, but it's quite rare to see very large caches on a CPU chip because you have a design constraint. You only have so many transistors to spend, and the more you spend on cache memory, the less you can spend on other things. So because of that, you end up with this hardware architectural problem that you have gigabytes upon gigabytes of main memory, but you can't make the caches much bigger. So that's why it's actually a hardware problem rather than a specific Java problem. And the other point to remember is that Java is 25 years old now. It's a very good language, but it has the way I always describe it is that it's a very far-sighted and opinionated language from 25 years ago. And I think most of the major design bets that Java made have paid off in terms of processor architecture independence. That turns out to be a winner, because despite the fact that we had a long period of time with Intel, it turns out not to be too difficult to move Java to other environments, which is really useful. The idea that you actually have built-in garbage collection. Virtually every language has built-in garbage collection now. The only language that doesn't really have some sort of GC is C++, because they do backwards compatibility things, and it would be, I think, problematic. And Rust. And it's not that Rust doesn't believe in GC, but Rust's trying to push the envelope about garbage collection and memory management in a very different way. So you know, for most general purpose application programming languages, you know, the design principles of Java really have paid off. And to the point about making everything by reference, if it's an object, treating all objects by reference and insisting on an object header makes it easier to implement garbage collection and a lot of other things besides. So the fact that the Java memory model is so simple, you have primitive types on the one hand, and you have references on the other. And every reference points into a well-defined Java heap, and every reference points at the start of a Java object header, is actually a really good model. Now, is it starting to show its age? A little bit, potentially. That's why we have things like Project Valhalla and an attempt to do things to increase memory density and to increase alignment with the way that modern hardware works. But the model, I think, has persisted, you know, extremely well for 25 plus years. Okay, some great questions. So let's come back. And how are we doing for time? Oh, we're at the 1 hour mark already. I can't actually remember how long we were supposed to stream for tonight. So we'll just keep going and see how we go. So we've talked about the subsystems, and let me start with some Java Mission Control stuff. So I keep calling it Java Mission Control. I know that I'm actually technically supposed to be calling it JDK Mission Control these days, because the names have changed and something about trademarks. And if you haven't used this program before, there's kind of an interesting pair of programs that exist. So the one I'm showing now, when the display decides to wake up, is JDK Mission Control. And JDK Mission Control is a GUI application, as you can see, which is not working today. Okay, let's try starting that again. See if that will come back up this time. Occasionally that I see problems with JDK Mission Control. It might be the case that it's picking up the wrong version of Java to start with. I have seen that before. If not, I will do something else involving the other piece of the technology, because let me talk to this and see if it unsticks itself. JDK Mission Control is a GUI application which allows you to look through a recording file. So there are two pieces to it. There's the viewer, which is Mission Control, and there is also the file generator, which is called Jdk Flight Recorder, or Jfr. And as Mission Control has decided it doesn't want to play ball today, we're going to take a look at that instead. So here's one I made earlier. So this is my local desktop. And as you can see, I've got a few files which with a file name which ends Jfr. Make sure I'm switched into Java 11. And let's just say I'm going to show the Jfr tool. So the Jfr tool basically allows you to look at and to manipulate recordings. So I'm going to do this from the command line rather than showing Mission Control, because it's not playing ball today. So let's, for example, take a few of these. I think I'm just going to Yeah. And this will just go through and it's going to print out a whole bunch of CPU counters. And if you look carefully at this, you can see that there are, there are loads and loads of these. I just press this. So this file started at about 2 o'clock, 17 minutes past 2. And what you can see is that it's got 3 readouts: the JVM user, the JVM system, and the machine total. So this is an automatically generated event which has come from within the JVM itself. So the JVM is outputting these telemetry events which show how much CPU it's using. There are actually 130, over 130 now, different types of events that are present in the JFR format. And you can configure your JVM to actually produce a file containing these outputs. And then you can use tools like Mission Control or Jfr to actually step through it. So, and this goes on, and if I go all the way through. So this file recording is about 2.5 hours. Started about 2:17, it finished about 4:30. So you can see that there's a good couple of hours there, and it's picking up some of these events, like there's the user in the system. So those are kind of regularly cadenced, and if you look at the timestamps, you can see that it's ticking about almost exactly once a second. So it's got quite a few events in it. And this time let's look at a different event type. Let's look at garbage collection events. Okay, look at those. So now you can see all the different GCs that it's doing. So it's using the G1 garbage collection, and this is a new collection. And you can see that it takes about 3 milliseconds to do a collection of the heap. And the ones which say G1 new are obviously the young collection. There's also probably some G1 old and some mixed in there as well. And you can look at the timestamps and you can see that about every 3 seconds, it's pausing for about 3 milliseconds. Yeah, so the gap between that one and that one is about 4 seconds. So that gives you some idea. You could take this data and you could actually use it to, this tool is just printing it out. But if you had access to the file format, you actually could produce something else. You could produce, I don't know, just some JSON or some CSV files to have a look at. So you could actually use this to generate some data. So let me bring back the IDE. And let me show you this. So I've just done the thing where it's confused my keystrokes and collapsed a bunch of my methods. Never mind. I'll just have to go back through and reduce all these out. So here is the main method down here. So I can pass this a file name, and it sets up this JFR file processor, and then runs this main piece of the method here. And if I just show you the import statements, you can see that there are a couple. Jdk.jfr, consumer recorded event and recording file. These appear in Java 11, and there is a backport to later versions of Java 8 as well. So if you're using Java 11, great, it should be there. If you are using Java 8, you really should be looking at the latest one. So let's see how this runs. Let's get rid of this. So the core of the program is here, and I start off when I get the recording file, which corresponds to the file with all my events in it. There's a method on it called has more events. So we're just going to while loop. We're just going to spin over the file and picking up each event as we go. So we read a single event from the file, we check to make sure it's not null, and then we perform a decode on it. And let's just see this in action. It helps if I actually run the right program and not the one that we were just running. Okay, what else have we got? Jfr file processor. There we go. Much more interesting than the string hashing program that we've already looked at. Okay. So there's a whole bunch of data that's just coming out here. So let's just stop that and look at some of the output. So look at some of the data we have in here. So what we're producing, well, we have this map, and it's producing a little map which has got a class name, a start time and end time, a TLAB, which is a size, and an amount of object size that we asked for. Oh, and a thread name. So you can actually see which of these threads are causing these events. And the event name is object allocation in new TLAB. So one of the secrets about the way that the JVM actually allocates memory is that each of your application threads is given a private buffer for new objects. And that's what this phrase TLAB means. It means thread local allocation buffer. So the thread that your code runs so is stored. Sorry, let me start that again. The code that your thread runs is provided with a private buffer for making new objects in. And that means that individual thread doesn't have to worry about whether or not another thread is allocating in its space. So it has the whole buffer, and it can just keep moving further and further along in the buffer as it goes. So that means that at some point, the thread, if it's allocating a lot of objects, may run out of space. So it may need a new buffer. And if it needs a new buffer, this will trigger an event where the JVM provides a new TLAB to the application thread. So that's what we're doing here. We're asking the JVM to tell us about these new TLABs as they're created. So as a thread is provided with a new TLAB, we want to look at the event which occurs, and the event will have some metadata on it: what time this happened at, which thread caused it, which class caused it, and then the sizing and the TLAB. And that's what turns into the output that we see here. So there's a couple of other things to notice about this, which just for funsies. First of all is the decode event, and what we do in that is, well, we have a thing called mappers. To pass in the event, we have a thing called mappers, and we loop over the contents of mappers. Notice it's mappers.entrySet, and as we've set it up here, mappers is some sort of map object. So we take the key and we apply a test to it, and if that passes, we transform it using the apply. And this is kind of a bit of slightly unusual, almost functional programming in Java. I find that when I'm writing my code, a lot of it tends to be, well, slightly functional programming, because what my map consists of is it has a key, which is a predicate. And a predicate, if you've used Java streams and so on, is a function which takes in an object and returns true or false. Okay, so it's like a question that you could ask about an object. Is this object so and so? Yeah. So that's what we have. We have a questioning object, a predicate, and then the values of the map are functions. And the function takes in a JFR recorded event, and it returns a map of strings to strings. So the output, the strings that we saw down here, those are going to be the return values, the result of calling the function on the event which comes in. And then you see I've only got there's only one key and one value in this map. The key is something called test maker, which is a call to a static function, a static method to return the predicate. And then the function is defined as a lambda expression. So I don't know if you can see that, but that is all one function. So that first one is a predicate value which we return from this helper method. And then the second value, the value in the map is actually a lambda. So that code is a little bit unusual. That's not the sort of code that I think a lot of Java programmers would necessarily write, but it's kind of the way that I like to think about some of these problems. So what we're going to do is the test maker, just to finish off the description of the code, takes in a string and it returns a lambda expression. So this is what we would call in functional languages a higher order function. So the method test maker takes in a string and it makes a function out of it. So given a string, the function that it returns is a function which takes in a recorded event, and then it returns true if, when you get the event's type and get its name, it equals the value of S. So the value that we pass in here is jdk.object allocation in utlab. So what the function that gets made is it returns true if, when you apply it to an event, the event's name matches this string. Okay, and then down here we then, if that's true, we then take the event and we've basically determined, we've filtered out any event which doesn't match the type that we're expecting. And so we can then use the function that we've written here to get the values that we want for our hash. So that probably sounds a little bit abstract. So let's do another one. So okay, now what I'm going to do, so that was the first key and the first value. I'm just going to put in here, and that can go there like that. And I'm going to put in another key value pair. And this time I'm going to take in a different name string. So now I'm not going to look at the object allocation. I'm just going to look at something a little easier, which is the garbage collection events. And okay, we want start. Yeah, this one doesn't have an end time, but it does have a start. So let's do that. And what else is in there? Well, there's the name field, which tells us what time it is. And we've got a duration as well. So, and a name. So we just want to do get string. Okay, and that looks to me like that's actually compiled. So let's rerun that. Let's see what happens. So now we're going to be getting two different types of events. We're going to be getting the object allocation in TLab, and we're also going to be getting the garbage collection events, which are going to be a lot shorter. So let's just rerun that. Let's see. see what happens. Let's just zoom in a bit. Oh, there's a lot of noise there. So I think there should be some G1 new events in here. So let's just try and search for one. No. I can always cheat because what I can always do is just deactivate this first element just by hashing it out like that. And now let's rerun. Yeah, so there you go. You can see all of the different garbage collection events that are there. And now, we actually probably want to see what the duration is like. So let's try and grab that as well. Okay, and so put another field in here, duration, and just wait for Gradle to do its thing, rebuild, and rerun. And you can see that these are, well, it's come out as a duration. So this is a formatting of what a Java time duration will look like. You see, because the return value of duration is a duration object. Okay. So, and you can see that the durations of the garbage collections are, well, that will be 100 milliseconds, that will be 10 milliseconds. So they're in the kind of 2-3 millisecond range, which of course matches up with what we saw when we ran the Jfr tool here earlier on. So it's kind of fun that we're able to see and to reconstruct some of the same data. And this is real performance data from a real application. And of course, I've been fascinated by a lot of this stuff, for a while. So I actually have something a little special to show. I've just got to find the right tab. It's the standard problem. It's one I made earlier. Okay. Oh. Of course, it always helps if you actually do this in the staging environment and not in the production environment, which is why I couldn't find what I was looking for. So what I'm going to look for now is this is my work applications. This is a service that I built called BMDS, Basic Metadata Services, and this is what I actually do with Java Flight Recorder data. It's fun to play with it and to produce things which are are displayable and that you can produce some graphs and some stats. But actually, I've actually been working on a product which lets us see full details of what's going on. And this is the same data that we were just looking at. This is all of the Java Flight Recorder data. So here is the CPU utilization. I showed you JVM user and system and machine total. Well, here they are. And this is flowing from a real service in real time. So this will just continue and allow us to monitor and see all of the things which are going on the machine. Up here, we've actually got the flame graph, as it's called. And basically what happens is the width of the bar here shows you how much time is being spent in each of the different calls. So you can see that there is for example, there's a Kafka client that's running here. And here are all the subcalls, here are all the different stack traces which are going on. We're sampling that data and showing it off as part of the. So I'm really pretty pleased with this. This is showing me a lot of really good and useful information, and it's all built out of the low level working with Java Flight Recorder events that I just showed you. So we were talking about object allocation in TLabs. Here it is, and this is showing you that if I just take out my Kafka consumer service, that one is my thread, and it's allocating, well, between 100 and 200 megabytes per second. So I'm pretty happy with that. The thread CPU utilization is down in the 2 or 3% range. So this is all in all pretty healthy. And this is an extreme example. It took a team of us several months to build this. But it is all based on the Java Flight Recorder data. And this is an example of the kind of monitoring and the kind of insight into your JVMs that you can get. Oh, and I should mention, of course, that it's all open source code. So everything that I've just shown you in terms of the data gathering and collection is all freely available as open source code. So the transformers that I showed you and the trick where we test an incoming event and then transform it, all of that is used in a slightly more complex form in the real production software that we deploy. So the techniques and some of the things that I've shown you are actually genuinely real. And yeah, let me show you. Let me show you the actual GC collection mapper. So there we go. There's the GC collection that we were just looking at. This is what it looks like in its actual production form. Once again, we have an apply, but if you notice, what we actually have is this interface. Let me zoom that a little bit. It takes in an event and it converts it into a list of metrics, but it is also at the same time a predicate. And the same predicate that we saw here shows that we saw in the earlier example shows up here in this case as well. So I think that is pretty much everything that I wanted to show today. I've gone on for about half an hour longer than I was intending to, but I think it's been fun. This is the book, and I think as a special treat, I just need to find. I have a discount code for you. So if you would like to hang on to the line for just one more minute, I can put up a code for the book as well. And the code is let me put it up. Not quite sure about that as a code. TWIT-EVAN40, and that will get you a substantial discount off the current state of the meet, and of course updates when we go live and launch the remaining chapters. Okay, everyone, thank you very much. It's been real fun, and talk to you soon.